We are talking about chapter 12 in this particular video. And so with a screen share, we should be off and running. So this chapter is on glaciers and glaciation. A glacier is any long-lasting mass of ice that forms on land and moves under its own weight. So it's a huge amount of ice, has to start on land, and that's really a deciding factor when we differentiate. Anyhow, starts on land, moves under its own weight. Lots of snow and ice compacted together. Glaciers cover roughly 10% of the Earth's surface, and about 85% of the glacier ice is actually on the Antarctic continent, so down at the South Pole. The second largest area is up in Greenland. Remember, Greenland is that large island between North America and Iceland. And the remaining 5% scattered all around the globe in mountainous regions. So there are certainly glaciers in Alaska and Canada, New Zealand, China, lots of places on the planet have glaciers. They're just not taking up as much space as Greenland and the Antarctic. What is significant about a glacier is that they store a lot of fresh water. Glaciers store about 70%, 75% of the world's fresh water supply, which is one of the reasons why we're concerned about global warming. I know you've had this in school and you are well versed in it, but I will mention that what worries scientists is that if all the ice in Antarctica melted, world sea level would rise 70 meters, so that's 230 feet. And what that would do would actually destroy a lot of the small island nations in Oceania. So over in the Pacific Ocean, there are lots of little small islands that are not necessarily very high above sea level. And so the end result would be that as sea level increases, those lands run the risk of saltwater intrusion. So the plants that grow there would have their roots going down into salty soil. And the people may eventually just lose their homes altogether. They would become climate refugees, people who live in a country that no longer exists because of climate change. And then you wonder, where will they go? So it's a political as well as moral issue that has geologic implications as well. This graphic shows you a map of North America, and if you look really closely at it, you will see an outline in white and areas that are blue. This is showing you what would happen just in North and Central America if there was a rise in sea level due to the melting of those glaciers. And so you can see that the poor state of Florida would be underwater, that Charleston, South Carolina, Norfolk, that New York and Boston would be underwater, New Orleans, poor Arkansas, it just goes all the way up. The coastline would certainly change over time. So it's worth considering, you know, what are we going to do if we don't get a handle on all of this global warming and rising of sea level? It may not happen in your lifetime, but it is certainly a possibility. So let's get back to glaciers now that I've made my pitch for think about turning off lights and doing other things to reduce greenhouse gases to cut down on global warming, consolidate your trips to the grocery store, don't drive unnecessarily, and so on. All right, so here's a graphic showing a large portion of the planet and the major ice caps. So here is Greenland. Again, this little island right here is Iceland. There's certainly glaciers in the Himalayas. There are glaciers along the western coast of North America and the western coast of South America. And certainly there's a large glacier down here covering the South Pole, the Antarctic continent. There's land under all that ice. Let's look at the different types of glaciers. You have glaciers that start out in mountainous regions. They're called valley glaciers or mountain glaciers or alpine glaciers. They originate in pre-existing stream valleys, and what they do is they take the stream valley that was a V shape and make it more wide at the base to be a U shape. So they widen it out. It's really pretty easy for a geologist to tell a valley that was carved out by ice when compared to one carved out by water. A nice shape, one carved out by ice will always be very wide at the base. One carved out by water tends to be very narrow at the base. So here we have a photograph showing a master glacier, which would be down here, the master glacier, and all the little tributary glaciers join up with it. This is called a hanging valley. It's an elevated area above the master glacier, and we'll look at this more in lab. So these glaciers join with each other. You'll notice the black streaks in the ice. That is rock that the ice has broken off and dragged along with it. So we said we could have alpine glaciers or mountain glaciers or valley glaciers, all three names for the same kind of glacier that starts up in a mountainous region. You can also have ice sheets or continental glaciers. These originate in flat areas. They're not restricted to a valley, and they spread out in all directions. Continental glaciers or ice sheets are really large, as you can see the numbers. If you have a smaller area, you have that's also flat, it's an ice cap. And they're just smaller than ice sheets, and there are a few of those left in Iceland and parts of Canada and other places. This is an aerial view of Greenland. You can see that here is the ice sheet, and here are the glaciers moving down. This is the ocean, and this is exposed rock around the outer edges. The amount of rock that's exposed is seasonal. In the wintertime, obviously, more of this area is covered with ice, and in the summer and early fall, it melts. So let's talk about how glaciers form. They form when snow and ice get compacted under pressure, and what they do is the snow actually changes and turns into something we call firn, F-I-R-N, into firn, spelled with an I, because the ice actually changes texture under pressure. It looks different. So this ice will recrystallize as you apply pressure to it. And as your pressure increases, it changes over time. So we'll look at this graphic where you see a cutaway. You've got fresh snow on the top, and there are little people up there. And as you see down, you go down, 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 the texture of the snow actually changes. So it starts out with snow with a lot of open spaces. It gets compressed and turns into granular ice, compressed a little more, turned into firn, compressed even more, it's turned into glacial ice. And you can see the size of the particles that it's made out of just get smaller and smaller and smaller and more compact as you go down. When we look at a glacier, we talk about its budget. So how does the snow, how much snow piles up and when? It helps us discuss the growth and recession of a glacier over time. So glaciers have three possible stages of development. You have glacial equilibrium, where the amount of snow and ice that are added equals the amount that's taken away. You would call this a balanced budget. You have glacial advance, where the terminus, so the end of the glacier, actually moves forward because you add ice much faster than you take it away. This typically happens in the winter time, and we call this a positive budget. And then you have glacial retreat or recession, and this is where the terminus or the end of the glacier actually moves inward. So it goes closer and closer to the head of the glacier. Your glacier is shrinking over time. You are losing ice much faster than you are replacing it. And we'd refer to that as a negative budget. And typically we think of it as a summer phenomenon. So with any glacier, you have zones of accumulation where the glacier ice is added, usually in the center for an ice sheet or for a mountain or valley glacier up high in elevation. You have zones of ablation, which will be the lower part of the glacier where you lose the ice. And then there's an equilibrium line where the two meet each other. So again, a graphic. This is primarily from mountain glaciers. You can see we've got our little red line for the equilibrium line. North of that, I'm sorry, not north, above that at higher elevations would be our accumulation zone. Below that at lower elevations would be the ablation zone. So how do glaciers lose ice? There are three processes. They can lose it by melting. Again, climate change is a big culprit here. They can use it by evaporation. There are some places where the air is so dry that ice will actually go from the solid to the gaseous state. And then they can also lose ice by the formation of icebergs. That is referred to as calving, C-A-L-V-I-N-G. So the breaking off of chunks of ice to form an iceberg is called calving. The end of the glacier or the terminus or the snout is where those icebergs form, and it moves backwards towards the land as you make these icebergs, or as just you have ice melting. So you have global climate change, leaving most of our glaciers in recession. I'm sure that's not a mystery to you. You're aware of that. What we've got are some photographs that show you icebergs in the same location, but many years apart. So the photo on the left is from 1958, and the one on the right is from 2003. And you can see in 1958, the ice extended this far, but in 2003, it's way back here. We have a second photograph. The one on the left is 1941. The one on the right is 2004. You can see here's the mountain in the distance. That would be this right here. The ice is way back here in 2004. So way back here. All of this ice in the foreground has melted. And now we've got a lake there. Here's another photo. The one on the left is 1978. The one on the right is 2004. Again, this area is a lake. So let's see if I can get my bearings on this. Seems to be the ice. We're right here looking at it. So again, this whole ice in the foreground has melted and resulted in this lake. These photos are from the National Snow and Ice Data Center. It's a wonderful place to get more information about glaciers. So let's talk about the movement of valley glaciers. The previous discussion was primarily about mountain glaciers, but if you've got, we're moving and talking about how those glaciers now move. So they're trapped up in these old river valleys. You've got rock on the right and rock on the left. What happens is as they move down from those high elevations to lower elevations, the ice on the outside edges is kind of gripped in place by the rocks in these valleys, these old river valleys. And the ice in the center actually has more movement, more mobility, because it's ice rubbing against ice. So glaciers do move downhill. These mountain glaciers or valley glaciers move downhill. Fastest one's 120 meters a day, so that's almost 400 feet a day. The slowest one's only a centimeter a day, which is less than half an inch. So let's look at our little graphic. Again, we've got rock on the left and rock on the right, and this little blue line is the outline of the ice. If we put 3 poles or markers in the ice and then came back much later and looked at it, the one in the middle would have moved the most. because the ones on the outside, the ice on the outside edges are being gripped by the rock, and it's the ice in the middle that moves the fastest. So we do know that ice becomes fluid or plastic under pressure and actually can flow a little bit. If we looked at a cross-sectional view, if we sliced down through the glacier, through the rock, and looked at it on the side, we would see the rock that the ice is on top of. Immediately over that rock is what we call the plastic zone. This ice actually bends as it moves downhill. And then on top of that, we have the rigid ice, and that ice is brittle. It's brittle, and in fact, that's where crevices or crevasses will form. These are deep cracks that go down into the ice. As it moves from a single elevation and makes a sharp drop, the ice tends to crack. So these crevasses or crevices can be as much as 40 meters deep, so over 100 feet deep. I know these photos are not very good. I apologize for that. But the funny little places you see in the ice as it goes from up high to down low, as it changes from being almost horizontal to a vertical drop, those changes in the surface are crevasses. They are really dangerous. If you're doing any exploring, you want to check for them, which is why a lot of times people on mountain glaciers will carry poles or sticks that they'll poke into the snow and ice in front of them before they put their feet on them. Here is a photograph of a crevasse. What they'll do sometimes is they'll throw a metal segmented ladder across it and then climb across. And a side view of one. Here's a photograph showing you how the ice is broken up and the distinctive blue color. We'll see more of that in some videos. And again, another view of a crevasse. So basal slip and surges. Basal slip is the slow movement of the glacier because of pushes from ice at the head of the glacier, at the start of the glacier. Upstream, it pushes down. And a surge is rapid glacial movement, and that's because there's water under the ice. Where did the water come from? Well, as the ice moves over the rocks, it produces friction, and that melts some of the ice directly above the rock and causes it then to surge downslope rather quickly. Now let's move on to those ice caps and ice sheets. They are really thick. They're characterized by being several thousand feet thick. We call glaciation when the ice sheet grows and deglaciation when it recedes or shrinks. Greenland is not very green. About 80% of the island is covered in ice. That is a huge amount, and it actually weighs down the center of the island. If all the ice on Greenland melted, the island would be higher in the middle than it is right now. We've got some videos again. I can't screen share those, so I'm going to put them as a separate assignment. If we look at a North Atlantic iceberg, it would be shaped like this. So you'd have this jagged, sort of more narrow and tall piece of ice with most of it underwater. Looks like the way most of us would draw an iceberg. North Atlantic icebergs tend to come from these ice sheets in the North Atlantic. And we'll have videos of them breaking off and calving. There are some wonderful ones taken of people who went on cruises, which is really the best way to see the iceberg formation. If we go down to the Antarctic, to the South Pole, again, about 85% of the Earth's glacier ice is there. It's a huge amount. It is really thick. It is enormous. And it's really old, 40 million years old. That is some seriously old ice. So let's look at what happens with that ice when it breaks off. You don't get the same kind of iceberg. Instead, what happens is it's a multi-step process. So Here is the Antarctic continent down here, rock. And here is ice on top of it. So here's the ice sheet as it moves down and out. It forms an ice shelf. An ice shelf is where you've got ice that's attached to land, but it's sticking out over water. So this ice shelf will move out, and when it finally becomes so heavy that the water can't support it, it actually breaks off and starts to float away. And the part that breaks off, it starts to float away, becomes an iceberg. And they don't look like the icebergs in the North Atlantic. Again, we'll see a video of it. I'll put that in the assignment for the chapter. But they sort of look like enormous square ice cubes. They are really big. They're kind of flat on top. Now, over time, they'll begin to melt and break up, and they won't maintain this distinctive shape. But again, most of the ice is underwater, but again, huge and flat and straight sides. So that's what a South Atlantic iceberg would look like. And then this is a photograph. Again, straight sides coming up and flat on the top. And again, over time, it's going to melt. So the Antarctic, again, down at the South Pole, has two ice sheets, the west ice sheet and the east one. They are separated by the Transantarctic Mountains. I'm not sure all of us knew there were mountains down there. What another surprising feature is that there are at least 70 unfrozen lakes under the ice sheet down at the South Pole. So where do these lakes come from? Well, ice is a good insulator. Think to igloos. Ice is a good insulator. Think to fish under the ice. I know most of you probably haven't been ice fishing, but you go far enough north, the lakes and ponds will freeze over, but the water underneath the ice is still liquid. So ice is a good insulator, and in fact, as you go down, 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 the pressure of the ice actually decreases the melting temperature. So instead of being at 32 degrees Fahrenheit for it to melt, ice under pressure can melt at 25 degrees Fahrenheit. And so again, as the ice moves over the rocks, it creates friction, and that heats things up. And then you've got heat coming from the center of the earth moving up due to geothermal processes. So all of that is responsible for those 70 unfrozen areas, those 70 lakes underneath the ice sheet. Let's talk a little bit about glacial erosion. Rock flour, F-L-O-U-R, like flour you would cook with. Rock flour is ground up bits of rock that the glacier picks up and carries with it. What is significant about that is it's this rock flour that gives a glacial lake its distinctive color. Just like our Lake Hickory looks muddy because of our clay soil, a glacial lake is going to have a sort of milky blue color. I always think they look a little bit like really finely washed out denim. Some of them have a real pretty pale turquoisey color. I promise you could tell a glacial lake from a non-glacial lake by the color of the water if you were flying over it. They look very different. So the little bits of rock in the water scatter the sunlight, and you end up with this really pretty blue color. So when a glacier does deposit material, certainly you have the rock flour that ends up usually in these lakes and streams, but you can also have till. Glacial till is the unsorted, unlayered rock debris that a glacier dumps when the ice melts. So it's just spread out over an area. A lot of times it'll look like somebody's come in and taken a truckload of rocks, big and small, and dirt, and just spread it out. It is amazing. And then you can have erratic boulders. These are larger rocks that get broken off and carried by the glacier. So these things can be 12 or 15 or 20 feet high and that big across. And they didn't start out life in their final locations. Again, the ice broke them off and dragged them along, and when the ice finally melted, it dumped them. These are from Canada, but it's not the only place you find erratic boulders. So let's talk about where those glaciers come from. We've had actually 4 major ice ages, and we are currently in one now. An ice age is a period in time where there are large land-based areas of ice. So we've got Greenland and the Antarctic to put us in an ice age. I'm just grateful it's not a very cold period of that ice age. The last great North American ice sheet melted away from Canada about 10,000 years ago. So that was at its peak about 18,000 years ago, and the ice extended down into the US as far as Iowa and Pennsylvania. We'll look at a little map. You can see here the edges that show, you'll notice this is Long Island, New York, so the glacier extended that far. Oh, here we got North Carolina, Virginia, West Virginia, here's Iowa, Indiana, Illinois, Minnesota, all of this part. This part of the United States was covered in ice, and in fact, it brought topsoil with it from Canada. And when the snow and ice melted, the topsoil stayed behind. So what causes an ice age? Well, changes in the Earth's orbit will do it. This is a little more complicated than we really want to go into, but you'll just have to trust me. Increases in atmospheric CO2 actually change temperature, and that can impact ice formation. And then shifts in the continents because of tectonic plate movement. The land and the water heat up and cool down at different rates, and depending on how the land is situated with respect to the oceans, the circulation patterns that are set up will impact weather and can result in an ice age. And then certainly plate uplift. The glaciers we find in the Himalaya mountains are there because of the tectonic plates pushing the mountains up to higher elevations. So what are some effects of past glaciation? Well, the soil, I've already mentioned the soil in the central US being brought down. Long Island, New York is actually made from terminal and recessional moraines, so the glacier pushed that area into place. And there are some rocks in Central Park that are actually erratic boulders. Cape Cod is formed from moraines. All the little lakes in Minnesota are primarily formed from kettles, which were formed when the glacier passed over and then the ice melted. And the Great Lakes are a result of glacial action. And as we've said, the last ice age, glaciers covered 32% of the total land area on the planet. That's a lot of ice. So we will stop, and you'll want to be sure to watch the video assignments.